This is the conference for the C++ community. Here we get to discuss with the standards community and with all of the innovators that are building C++ now and for the future, the innovations and opportunities that we have in our company, as well as the opportunities that they're exploring as an industry.
Okay, I think it's time to get started. So first off, good afternoon, everyone. Thank you for coming to my talk. My name is Paul Gesel. Today I'll be discussing code generation from Unified Robot Description Format, known as URDF, for accelerated robotics. Before we get started, just a few things about myself. For one, this is my first time attending CppCon, so I'm glad to be here. And to make it even more special, of course, it's my first time presenting at CppCon. About me, I'm a robotics research scientist at Picnic Robotics. On my day-to-day work, I often use C++ for robotics algorithms. And additionally, I earned my PhD in computer science from the University of New Hampshire in the area of robot learning. So this is a concept slide of what I'm trying to present here. First, on the left, we have this URDF, which is an XML-based file format. And essentially, the URDF is a declarative syntax to describe the kinematic structure of your robot, including the number of joints, the links and their geometries, and the joint types. And with this information, you can do forward kinematics, you can do collision checking, and this is sort of the standard format to describe robots. And with this well-formed syntax, we can actually run it through a code generation process to translate this into C++ code, into optimized C++ code that can be compiled on the user's CPU for certain performance enhancements. So this is the overall outline of my presentation. I'm going to start with some background, just background in general of robotics, including some of these commonly reoccurring subroutines like forward kinematics, inverse kinematics. And then I'll move on to motivate the problem. So the question is, why would you need code generation, or what situation are you really going to get benefits from it in? Then I'll move on to the actual implementation detail of a library I've been working on called fast forward kinematics. And this is a GitHub repository. I'll have a link at the end of the presentation where you can check it out. I'll discuss the build process for this library, and then also discuss some code implementation details and some design decisions I made for to try to get the best result out of the forward kinematics and inverse kinematics implementations. And lastly, I'll discuss some results. So I made a few simple benchmark programs, and I'll show the perf results for my code-generated forward kinematics compared to an existing library called KDL, which is a fairly popular robotics kinematics library that's open source. And lastly, summarize with just a few points on lessons learned. Okay, so moving on to the background. In robotics, sort of a fundamental skill of an autonomous system is to do motion planning. So that's what this slide is trying to show. On the left is some arbitrary start state, and then we have a goal which says, oh, the robot is supposed to move through some scene with obstacles and make some final position to reach the cube. And this problem of finding a space in this scene without colliding with the obstacle, that's robot motion planning. And then just a high-level overview, we can sort of describe this motion planning problem as thinking about all the possible states the robot can be in, and the robot's state is fully defined by its joint angles. And for any given set of joint angles, we have like the start set in the top left, there's the goal set in the top right, but there's many, many intermediate possibilities. For example, if we take a straight line through the joint space, in this case, there would be a collision with the obstacle shown in the top image. And then, if we find the right path through the joint space, we'll be able to navigate the robot arm around the obstacle. And this is a simplified example. In general, we might wind up sampling this space thousands of times for a simple problem, or tens of thousands or hundreds of thousands of times for more complex problems. And each one of these points in this graph often requires calculating forward kinematics, collision checking, nearest neighbor lookup. So these are these commonly reoccurring algorithms in robotics that ultimately wind up being the bottleneck for motion planning problems. This is just a brief summary on forward kinematics. So the problem of forward kinematics is, given a set of robot joint angles, calculate the 3D positions of the robot links in space. And there's really two components to this. One is to calculate these transformation matrices, which are a function of the joint angles. And then step two is to multiply all of these values. And that's enough to calculate the link positions. And then there's inverse kinematics. So there's a few ways to do inverse kinematics. Oftentimes it requires calculating the Jacobian of the robot model. And just a brief note on what inverse kinematics is. You see in the animation on the right, I'm able to specify a position in 3D space that I want the end effector to go to, and the robot will go there. And then I can sort of servo it around in 3D space. So it's a very useful problem. To achieve this, we often have to calculate the Jacobian. And this is a matrix which you can fill in like this. So each column of the matrix is going to be related to the joints and the joint axes. So in this case, I'm looking at joint 1. And if I'm rotating about joint 1, it has some effect on the end effector position. It would rotate around this purple circle. And there's this black arrow showing like the direction it moves when you change that joint a bit. And that direction is going to be used to fill in the Jacobian matrix. So you can calculate this by taking distances between these joints and using like a cross product. And then you loop through all the joints in the robot model, and you can fill in this matrix. So that's one way to go about calculating the Jacobian, which is often used in inverse kinematics algorithms. So moving on to some motivation, like this is sort of the goal. So I was saying the motion planning approaches, they're computationally inefficient. They might have 100,000 expansions, and you're not going to be able to do it in real time. But if you can optimize the algorithms and maybe do some shortcuts in other places, this is the result we want. Real-time motion planning in a fully dynamic scene. And you can see in this case, like when the object is moved up, the robot will swing its arm underneath. And when it's moved down, the robot will plan over. So this is the capability that we want, and we don't want the implementation on the code side to get in the way of this. This is just repeating a few of the points I made before. One thing to note is that the library I'll be discussing for CodeGen, I'm not specifically doing collision detection or nearest neighbor lookup, but collision detection, nearest neighbor, and forward kinematics, those are all going to be crucial to do planning like that with a sampling-based algorithm. And I got interested by this idea and was first exposed to it when I saw this paper from researchers at Rice University that they call motions in microseconds via vectorized planning. And basically what they did is took a URDF format and developed a novel compiler to translate that format into C++ code. And in some cases, they were able to beat the state of the art by 500 times, which is obviously a huge improvement, and they're able to do real-time motion planning. And again, there's some caveats, but their approach essentially was optimizing the actual generated code, the layout of this memory, so they could do SIMD instructions, and they could do many forward kinematics in parallel and collision checks in parallel. And then there's also some information that if you have at compile time, you can like unroll loops, you can skip calculations of fixed joints and things like that. So yeah, once I saw this, I got interested by this idea and I started investigating this project. And like I said, I made sort of my own version, which does some of the things they implemented. And this slide is just some more just general detail on code generation. So in the ideal case, I guess we would have an engineer develop a customized and optimized kinematics per robot, but that's not really scalable. So code generation is sort of a trade-off between these two things. So we get to use a little bit of domain knowledge, like the URDF. The number of joints can be fixed, for example, and any redundant calculations can be eliminated. So we have some of this domain knowledge, but we're automating the process, so we kind of get a middle ground. And then additionally, if we can sort of show that the code generator meets some sort of certification, like maybe the generated code doesn't allocate memory or it's real-time safe or something like that. Once you can sort of validate that on the code generator, then you can generate these kinematics for different robots, and you'll meet those same, you'll sort of inherit those certifications. So that's just the benefit of code generation in general. And you'll compile the generated code on the client CPU, so you should be able to take advantage of all CPU tuning possible. And then one last thing is that compared to, say, a templated robot builder API, like you could probably get many of the benefits in terms of the compile time optimizations, but then you have to maintain this code yourself. And potentially you could make mistakes. So if the process can be automated, that's beneficial. And additionally, there'll just be less code to maintain because these URDFs are often maintained by the manufacturers of the robots. Okay, so moving on to the build process. So here's a simple CMake project that sort of shows how a consumer of this library would use it. So first, they'll just create their executable. In this case, it's called forward kinematics test, and it depends on a CPP file called forward kinematics test.cpp. And then they'll call this CMake function called generate fast forward kinematics library, which takes in 3 arguments. One is the name of the URDF file, and then it also takes in a root and a tip link. And the reason this is necessary is that the kinematics sort of approach that I showed earlier, where you do multiplications of these matrices, that's for a robot chain. And if you had, say, a dual arm robot, you'd have a different kinematics algorithm per chain in the robot, per sequence of joints. So in this case, I'm just looking at a single robot chain. And then after running that, it generates a target called fast forward kinematics library. And the client just has to link to that library and it will automatically run the code gen, build the project, and they'll be able to call the functions of the generated code. So just go over this sort of function in a little bit more detail. First, we try to find the Python interpreter. If it's found, we'll print out where the Python executable is, which could be useful for debugging. And otherwise, we'll have a fatal build error, which will stop the CMake build. So the reason why I'm using Python is because I'm generating the C++ code using Jinja templates, and I'm using Python to render that code. Then after getting the Python interpreter, I'll run this execute process. So this script is relatively simple. It's just going to count up the number of joints in the robot chain. And it's going to take that value and print it to standard out. So execute process has this output variable option where you can capture the output of standard out into a variable, which I'll use later on in the build process. And this is what the script looks like. It's pretty simple. It's just taking, it depends on arg parsing and a URDF parsing library. Checks the input arguments, makes sure we have the correct number. It will load the URDF file into memory using the URDF loader library. Then it just loops over all the joints from the base to the tips, counts them up, and then prints it to standard out into this variable called fastfk number of joints. And just to give an idea of the scale of these URDF files, and if you haven't seen one before, they can often be hundreds of lines. So in this case, I'm just looping over all the joints to give an idea of what's going on here. So that script would go and count those joints and output it into this variable. Okay, secondly, to run inverse kinematics, the algorithm that I implemented here is an optimization-based algorithm. So we need a mathematical optimization library. So in this case, I'm including an external project from GitHub, and it's based on the LBFGS solver. One nice thing about this library is it's a header-only library. So we're compiling the solver with the same optimization options as we're compiling the forward kinematics with. So it's just beneficial for performance. Then we get to the actual code generation step. So here it's adding a custom command and running a script called robotgen.py. And this one takes in a few arguments. Again, the URDF file, the base link, the tip link, and then a few extra arguments. One is going to be the Jinja template, which will be used to render the C++ code in. And then secondly is the output file name and the location. So here I'm using, on line 36, the CMake current binary directory to write this file to. I've added dependencies on the URDF file and the Jinja template for this command, which is beneficial because if I pull in and update a URDF or I make some change to the template, I'll rebuild and this target will automatically rebuild. And on line 49, I have to add a custom target. In this case, I'm calling it code generation, which depends on the output of that custom command. So then if I say make code generation target, it will automatically run this Python script and generate the code. And I'll go over this script. It's relatively simple, but same thing at the beginning as before. We use argparser, make sure we have the right number of arguments coming in, load the robot model into memory using a URDF library. This is just a helper function. So anyone who's familiar with the URDF format, it specifies the joint transforms using positional offsets and roll pitch yaw. So it's just a bit more useful to have it in terms of transformation matrices. So this function just converts from roll pitch yaw and XYZ into a transform matrix. And then this step here, it collects all the information or it sets up the variables to collect all the information which will be needed to actually render the generated code. So I have the rotation matrices, the offsets of the joints, the types of joints, and then all the joint names. And then what happens here is I loop over all of the joints and check to see what type they are and whether they're fixed, and it will change the math on what actually gets added to this in the end. So for example, on line 56, 57, we check to see if it's a fixed joint, because if it's a fixed joint, we can actually just merge it with the previous transform and not even include it in the generated code. And then otherwise, if it's a revolute joint or a prismatic joint, there's slight variances on how this information is collected. And then one last optimization, which is done here, is just a check on sort of the potential for numerical precision issues. So any value which is close enough to 0, and I have a hard-coded value here, but we'll just set equal to 0. Because that way, at compile time, if the compiler sees 0 multiplied by something, it can just skip that step altogether. And then lastly, it takes all of those values that we collected from the URDF, and it, on line 87, renders those values into the Jinja template, and then finally writes the generated code to the specified location. So this is what Jinja template looks like for this project specifically. I won't go into detail on all the syntax here, but we can see like the rotations, for example, are specified there, and there's like offsets. And after rendering the code, it goes from the template into C++. And I'll go into a little bit more detail on the design decisions and like what each of these variables mean on a later slide. One additional thing is this is another Jinja template, but here it generates forward kinematics library for CUDA kernel. So I guess one of the benefits of doing code generation is that we can sort of have the same build pipeline and extracting information from the URDF, and then generate an entirely different language to run on the GPU and potentially get some benefits like that. So the only difference is here is there's now this global specifier in front of this function to specify it's supposed to run on the GPU device, and then a little bit of extra logic to find out which block of memory each thread is supposed to work on. And in the results section, I'll have a comparison with the CPU code, with the GPU code, and under a few different situations. So after this target is built, it's going to generate the code. And then what I'll do is I'll create that target fast-forward kinematics library, depending on the output of the generated code, forward kinematics lib.cpp, and add dependencies between this target and code generation and the lbfgs library. So that way, if you build this target, it's automatically going to download that optimization library from GitHub and run the code gen. And finally, the public interface for this library depends on eigen. That's just how I take the data in, so I have to find eigen, link to it. And lastly, this target compile definition for this variable which specifies the number of joints. The reason I'm adding a compile definition for that is just so I can use fixed size stack allocated vectors to represent the joints. This is what the build process looks like. You can see I'm running CMake, and I'm saying to put all the build artifacts in this local folder called build. And when I run this, we can see that found Python, it prints which Python's being used. And if I now check the files in the build directory, as you would expect, it's just the sort of standard CMake files. And then when I run the code generation target with make, we can see that comment gets printed out that says which script ran and what all the input arguments were for it. If I do ls build again, we can see there's now this generated code for kinematics lib.cpp. And finally, I can make this target fast-forward kinematics library. It pulls in the optimization library from GitHub, builds it, builds the generated code, all in about 10 seconds. OK, so moving on to the code itself. So what I wanted to do was compare the output of this generated code to the KDL library. So I just made this C++ interface so I could use the same test files and just change out the implementations. I'll just go through this. So first, we have this struct defining an IK solver stats. Essentially, inverse kinematics, it can fail. You can tell the robot to go to a position which is not possible. So this is just the return type I defined, which there's a variable called success, which can be true or false, and optionally a string to explain why your algorithm failed. And then just a few extra statistics to give information about the solver itself. And then the interface itself, I decided to use concepts to define. So there's a few different pieces which I combined to define the full interfaces. So this first one is this concept called kinematic interface constraint. And there's a few things I require. One, on line 23, whatever type you use, I want it to have a static expression method called getNumJoints to return me the number of joints. That way I can use the same code to allocate a fixed size array. And then I have setJoint and getJoint, just different overloads for different situations that I used in my implementation. Then there's the forward kinematics interface constraint. So this concept is defining forward kinematics. So essentially, you need to be able to call a forward kinematics function to propagate the transforms through the robot chain. And there's also a getFrame method, which takes an index and a transformation matrix by reference, and it's just going to write that data into that matrix. Lastly, there's an inverse interface constraint, and this one defines the method inverse kinematics. And notably, the inverse kinematics takes in a desired transform, which is the position you want the end effector to go to, plus an initial guess. So this is like the seed to start the optimization algorithm. And then the output is going to be a struct, which is the IK solver stats. And then I define these structs, which actually create the interface itself. So if we create this forward kinematics interface struct, it's going to have to be a type which implements both the kinematic interface constraint plus forward kinematics. And then if we create a struct which is an inverse kinematics interface, it needs to implement all three of those concepts. OK, so I'll go through the test files I used to benchmark some of this. So this one is for forward kinematics. The first thing I do is just check to see if I have this definition used fast kinematics set. And if I do, I'll include the header file for the CodeGen library. And I'll define this alias ki to define the kinematics interface according to its implementation. Otherwise, I'll use the KDL library. And I just I implemented the KDL library to conform to this interface. So for this test, what I want to do is evaluate forward kinematics at many possible random joint angles. So I just initialize a bunch of random joint vectors. And then I create the interface. So again, here it would switch either between the CodeGen or KDL, depending on the compiler definition I had. And finally, start a clock, loop over all these random values by some multiple, and call setJoints and call forward kinematics. And finally, at the end, stop the clock and print out some statistics on how much time on average was taken. Then there's the inverse kinematics test, which looks quite similar. At the beginning, same thing. Depending on a definition, which I was switching back and forth in CMake, I'll include a different implementation. A little bit of difference here. So for inverse kinematics, again, it can fail if it's told to go to a position it can't go to. So what's done in these few lines is to create a random joint angle, call forward kinematics, and that transform, you know it's going to be possible to reach. So this is just setting up an initial target position. And then I'll go and loop over some amount of iterations and call the IK solver on that position. And I'll give an initial guess, which is a random vector. So this is timing it. In addition to that, it's also counting the number of failure and success. And then prints the statistics. OK, so now I'm going to go over a little bit more detail on the actual code generation itself, or generated code itself, rather. So first thing is the memory layout. So what I decided to do was to pass in a contiguous block of memory of a specific size in order to do all the forward kinematics with. So data size is how many floats I need per joint. And there's sort of a comment, it's probably a bit difficult to see, but it says what value is supposed to be in each entry. So the first two are going to be the sine and cosine values of that joint angle. Then there's the positional offsets. Then there's the rotation matrix. And then this is going to repeat over and over for each joint. These are all the fixed rotation values from the URDF and fixed offset values. Notably here, the R_all is in row major format. And I tried putting this in row major in the following matrix, which multiply them in like row or column, and just tried different combinations to try to get the best result. In order to do multiplication of two matrices sort of in place, you can't do it in place. You need at least 3 additional pieces of memory. So I just create 3 slots to store all the temporary results in. And then this logic repeats. Again, this is code generated. This logic repeats for each joint, where it grabs the index that we're talking about. So of course, it starts on index 0. And then all of these reference values into the data array and into the fixed rotations and fixed offsets get created just to sort of keep track of things a little bit better. And so for the first joint, it's always in the frame, like the world frame or the base frame. So all you have to do is you have to calculate the rotation which is generated by that joint and write it into the data. For the next joint, it's going to be similar, but additionally, you also have to consider the rotation of the previous value, because you want to accumulate these rotations as you move through the robot chain. So that's what this R_old is on 133 through 141. Whoops. And then on 155 through 163, this is what I was referring to before. We're doing multiplication of this is setting the rotation according to the joint angles, like the previous joint I showed. And then this is where we multiply by the previous rotation to generate the final rotation. So this is just 3x3 matrix multiplication. And then there's a vector times matrix as well at the bottom. So in these ones are in column major format. So like I said, I tried different variations to try to get the best result. OK, so that's for forward kinematics. For inverse kinematics, this one is an iterative solver. So this overloaded function here, or the operator parenthesis function here, this is going to get called for each iteration of the kinematic solver. And essentially what's happening is it's giving, let's see, there's an initial guess Q, which says its current best guess of the values of Q, which will solve the IK problem. And the first thing we do is calculate the forward kinematics at that joint angle. So all what's being done here is it's setting the values into the data array, calculating the sines and cosines, and then calling this internal forward kinematics function we were just looking at. This part here is just setting up some of the memory that's needed to do the calculation of the cost function. And this one's the calculation of the cost. So what this IK solver algorithm is trying to do is minimize the distance between the target location and the current robot and effector location. So, and the solver needs to know the gradient of that cost with respect to the joints. So you can calculate that using chain rule, and there's just some notes in here to help remind me of like how this is done specifically. So the point is it requires calculating the Jacobian, which is like the animation from the slides in the beginning. So this requires looping over all the joints, finding the joint axis of rotation, and essentially doing a cross product between that and the end effector position, which is what's being done here. It's calculating the Jacobian and then multiplying by the gradient of the cost to get the total gradient. And that process just gets repeated for the number of joints in the robot. Okay, so moving on to the results. What I did was ran the test files I showed earlier with both KDL and the generated code, and then I just ran perf on it to find out how much time was spent in different functions. So interestingly, for the KDL library, we can see the total runtime of its own program, which are spent in each method. And I think what's interesting here is the amount of time which is spent in sine and cosine is only roughly 3.8% of the total runtime of the program, where the rest is spent doing matrix multiplications or doing that logic anyways to do the forward kinematics. When compared with this generated code, we can see that 40.8% of the time is spent doing sines and cosines. So a much larger percentage of the time is spent doing this expensive operation. So that's a good sign. And then about half the program time is spent in this forward kinematics function that I just went over, which is essentially doing all the matrix multiplications. So then we can look at the amount of time, the absolute amount of time on average it takes for forward kinematics. And KDL was running at about 350 nanoseconds, where the generated code was doing about 37.5 nanoseconds. And I think one part about this graph which is interesting is we can see the amount of total time spent with sine and cosine for either approach is actually approximately the same. It's just the amount of time that's spent in the actual sort of forward kinematics part of doing this is much lower in the generated code. And then I just repeated this for the inverse kinematics. So here's the perf results for IK with KDL. And here, majority of the time is spent in this Jacobi SVD, and that's just one of the matrix operations which are required to do the IK algorithm that KDL uses. So most of the time is spent in the actual IK calculations. And we can see the amount of time spent in the sine cosine as well. And there's actually a relatively similar result for the generated code in terms of the amount of time spent in the optimization. So this BFGS, this is sort of the optimization part. And then here we can see 5.7% is spent actually doing forward kinematics. And obviously there's a percentage of that which is spent doing the Jacobian calculations as well. So then we can look at the amount of time it takes to do inverse kinematics with KDL versus the generated code. And there's obviously very large savings on the forward kinematics, which translates to large savings per iteration of the IK solver. And then the BFGS algorithm, it tends to converge faster than the algorithm used by KDL, the LMA algorithm. So not only does it take less iterations, but each iteration's faster. So then the total runtime is averaging at 5.8 microseconds per IK solution, whereas KDL is doing about 119. Then one last result, this is the forward kinematics for the CUDA generated code. And one thing that's interesting is that if we just sort of naively take the code which was running well in C++ and have it run on the CUDA kernel, it's averaging over 450 nanoseconds per query, which is not very good. And that's if you do many, many robots in parallel as well. So the total amount of time it took to actually even get one result is, of course, would be huge. And the reason why is, I believe, the memory transfer speed. So if we take out, if we be a little bit smarter about the data that's being transferred across, so instead of having this data array that stores in the rotations and the positional offsets and etc. If we just give the CUDA code the joint angles and we have it calculate sines and cosines and such, it drops down quite a bit to be actually comparable with the CPU code. And if we completely eliminate memory transfer altogether and we just measure the time it took running the kernel, then it's dropping down to 7.48 nanoseconds on average, which of course is quite fast. Again, for many robots in parallel. And this is just the reference CPU code here. Okay, so summary and lessons learned. In robotics, there's certain algorithms which are really, really computationally intensive, and their subroutines should be the target of code generation or just trying to optimize your code as much as possible. Because if you can bring that down to a low enough value, then you sort of unlock this new potential, which is real-time motion planning. One thing is, obviously, if we do code generation, we have to leverage the fact that there's compile time optimizations in addition to CPU tuning that can be done for the actual machine that's going to run the code. And then finally, if you're going to generate code, try to make sure you generate it in such a way that it can take advantage of memory layout. If you can do SIMD, maybe you could do that. And then otherwise, the algorithmic improvements can, of course, also be included. So with that, I appreciate your time. Thank you, and I'll take any questions.
Hey, Paul, great talk. Thanks for giving it. I was wondering if you go back to the results, right? If maybe you could describe, how many joints each configuration had, and then you kept mentioning that on the CUDA ones you ran across many robots. So maybe discuss how many robots that was in their configuration.
Yeah. So these results are for the, I believe it's a 6DoF robot. I did run on a 7DoF and a 10DoF. Just the generated code, not all the KDF results. And it was pretty similar. Instead of 37 nanoseconds, maybe it was 40 or 50 or something. So sure. Not a huge impact by increasing the number of joints. And the funny thing is that IK might actually be faster, because if you have more joints, it's actually easier to find a solution. So the FK is always going to be slower with more joints. As far as when I say run many robots, I guess I don't mean like different robots, just like we give like a memory array of a few megabytes, and we say run all these robots at once. I don't remember the exact number, but over 10,000. So you can keep going up and up, and at some point it's gonna just plateau. Yeah.
All right. Thank you.
Can you imagine or describe a scenario where this might be useful for mobile robots? For example, planning a fixed number of steps ahead where the kinematics in each one, or for each step is known, a fixed time step and fixed velocity.
Yeah, so I think this would be very useful if you have an algorithm, right, that's gonna not run in real time, and this allows you to run in real time. So in mobile, like you're gonna run maybe A star as opposed to RRT. I feel like they're running that really fast already. Maybe if it was like 3D or drones or something. I'm not positive. I don't see why it couldn't be used for it though. If you had a mobile arm, by the way, then of course it would be useful.
Sure, thank you.
Yeah.
That's awesome. In your CMake example, you noticed, or you pointed out that you have to specify the tip of your joint chain. How does that look? Because then that ends up making, wherever the slide is. Basically, if you have exactly your scenario that you described, a dual chain situation that you want to generate each one of these for, like what would that look like in your CMake setup here?
Yeah, so I'm not positive if it would work currently, but what it should look like, ideally, instead of generate fast forward kinematics library, giving this target called fast forward kinematics library, you could also give it the name of like the robot maybe, okay. Or maybe it would automatically append the name of the robot to it. So what it would look like, what it should look like is you would run this generate fast forward kinematics macro twice, and you would just specify, oh, for this joint, and then you could just include the header for one chain versus another chain.
Perfect. Thank you.
Yeah. Yeah, if no one has any more questions, then thank you for coming to my talk.